we'll start. Okay. So we have seen during our last class that you generate double sideband suppressed carrier wave just by multiplying m of t, by a carrier signal cos omega ct. And we have seen we get double sideband suppressed carrier wave from this. We get double sideband suppressed carrier AM wave from this. Now, how to demodulate this? Simple process of demodulating a DSP SC AM wave is at the receiver, you multiply with the same carrier wave, with the same carrier frequency. Now, once you multiply, see what is the expression you get here. I told you this in my last class, right? So, once you multiply, just see what is the expression you get, right? See what you do, you multiply your DSP SC AM wave with a carrier wave. So, what expression you get is here m of t into cos square omega ct, right? After that, you are passing it through a low pass filter with a cutoff frequency. The cutoff frequency of this low pass filter is frequency of the message signal, right? Frequency of the message signal, that is B hertz. Frequency of the message signal, that is B hertz. The cutoff frequency of this low pass filter is B hertz. That means what it does, it will keep a signal with the frequency below B hertz. All the frequencies above B hertz will be removed, right? That means your carrier frequency is far more than this, right? So what will happen when this expression, right, when this expression is passed through this filter, low pass filter, which term will remain and which term will go out? This term will remain, right, and this term will go off. So what will remain is only half into m of t, right? This is what you require, right? So you got demodulated, you got the demodulated signal. Whatever signal you have modulated, you have demodulated it. This is the demodulation process for double sideband suppressed carrier wave. See here. This is what you get. Suppose if you put it in the Fourier domain, how can you convert this expression into the Fourier domain? This is very important, you need to remember this. How can you convert this expression into Fourier domain? Can you convert this in the Fourier domain? What is the Fourier transform of this? M of f, right? What is the Fourier transform of this? What is the Fourier transform of this? Come on, tell me. What is the Fourier transform of this? What is the Fourier transform of m of t cos 2 omega ct? How do you calculate Fourier transform of m of t cos 2 omega ct? Using shifting property. How to calculate this? This is very important, you are supposed to know this. You may get some questions based on that. How do you calculate Fourier transform of m of t cos 2 omega ct? I just want to come to that point now because signals and systems basics you all forgotten. If I ask you to find the Fourier transform of cos 2 omega ct given m of t and m of f are Fourier transform pairs. These are Fourier transform pairs. Okay, tell me, how do you calculate this? See, you can't get away with this. You have to do this. You can't get away with this Fourier transform. You will have to do. And it is not something difficult for you. Now, how do you calculate Fourier transform of this? Are you going to use that integration method? Will you be able to complete in this semester if you do that? You will never. That's why what you do, you just try to write this What is this? E to the power of j 2 omega ct plus e to the power of minus j 2 omega ct by 2. Now, this is, take half outside, okay? Then what you will have is m of t into e to the power of j 2 omega ct, okay, plus m of t e to the power of minus j 2 omega ct. Can you tell me what is the Fourier transform of this? Apply shifting property. You know m of t and m of f are Fourier transform pairs. Go back to your Fourier transform properties. Right? What are the properties of Fourier transform? Shifting property of Fourier transform. I have told you this in the last class. Shift in the frequency domain is equal to multiplication by an exponential term. So this will be m of, I can just put it in frequency, or you can just write it in the omega c, okay, omega plus 2 omega c plus this is m of omega minus 2 omega c. Yes or no? Right? Okay. The exponential term you are going to get it. You can either put it in terms of something like fc plus f plus 2 fc, okay, plus m of f minus 2 fc. You can put it in this term also, doesn't matter. Provided one term pi something will come here. Don't worry about it. Right, this is very important. Fourier transform pairs, it is given in the textbook. Just please have a look into this. Right? This is very important. You may get individual question like this to calculate Fourier transform. Right? It's very important. Don't neglect it. Fine? Okay? This is something you have been learning in signals and system. Signals and systems are very important for entire communications. These small things try to remember. Okay? Now see here. What is this, tell me? This is the Fourier spectrum of this signal, right? Now if you draw this Fourier spectrum, suppose your m of f is given by, I have already told you about this in my last class. Suppose your m of f is given by, I have already shown you that m of f, right? Hope you remember this, right? See, already in my previous slide I have told you what is your m of t and m of f. See, this is your m of t, this is m of f. Okay, this is your m of f. Okay. Now see here. This is the signal. Once you multiply m of t into the incoming signal, see, this is a demodulation process. I have already explained you about this, okay? So try to come early. I am not going to wait for more than 5 minutes. I will start my lecture as soon as I come. This is what you get, and you are going to pass it through a low pass filter. So once you pass this through a low pass filter, so what's going to happen? See, this is what you get in the frequency domain. So cutoff frequency of the low pass filter is B hertz. Now once you pass it through low pass filter, what will happen, tell me? This term will go off, right? This is low pass signal, this is low frequency signal. This will go off, sorry, what you are using low pass filter means this will go off, higher frequency will go off. Only the signal which is having less than B hertz will remain in the low pass filter, and all this thing will go, right? Now can you tell me what is this? Is it not the spectrum of the original signal? You got it back. After modulating, you got back your original signal. That's what demodulation is. See, demodulation in double sideband suppressed carrier wave is very easy, right? It's a very simple process, yes or no? Right? Demodulation in double sideband suppressed carrier wave is very easy. Even generation is also very easy, right? How does this both modulator and demodulator looks like for double sideband suppressed carrier wave? Simply multiplication, that's all. And the entire theory behind we have just seen now. You have a message signal m of t, this is a message signal m of t, multiply it with the carrier signal cos omega ct, you get here double sideband suppressed carrier AM wave. After that this is transmitted and once again multiply it with the same carrier signal cos omega ct, same carrier signal cos omega ct. So what you are going to get back your original signal half into m of t. Of course amplitude we can amplify it later. Done. This is your entire, this is a modulator and this is your demodulator. It's very simple. The theoretical aspects are also very important for you. Just read this. This type of receiver is called as coherent detector. What is meaning of coherent detector or synchronous detector? This type of, see, demodulation is also called as detector. There is a separate name which is same as demodulation. We call it the detector. Detector is also same, demodulator is also same. It is not different. Fine? It is not different. If I say detection, same thing. If I say demodulation, it is going to be the same thing. Have you understood this? Okay. Now, since we are using same carrier in the demodulator also, right? We are using same carrier in the demodulator. Yes or no? In the modulation, we are using cos omega ct. In the demodulation also, we are using cos omega ct. We are using same carrier, right? For modulation in the transmitter also, we are using same carrier. And in the demodulation, in the receiver also, we are using same carrier. Have you understood this? Okay. So, this type of detector is called as synchronous detector. Understood? Why it is called synchronous detector? Because you use the same carrier which was used in the transmitter or during the modulation in the demodulation process. That's in the receiver. It should be synchronized. Synchronized means same thing, right? Hence it is called as synchronous detector. Okay? It is synchronous detector. I've understood this. Okay? Synchronous. It's called a synchronous detector. Okay? Or it is called as coherent detector, where we use carrier of same frequency and phase as that of used in the modulation. Okay. Now, let us see how do we get the modulator. Okay. How do we see the modulator? Okay, just try to understand this. Hope you understood double sideband, suppressed carrier, modulation and demodulation. It is very simple. Okay. Now, here we use multiplier, right? Here is a multiplier. Mathematically we have seen, right? But how do we implement it electronically? It's a multiplication. It is not that your arithmetic multiplication, right? Mathematically it's okay, it's multiplication, okay. But how do you implement that multiplication using electronic device, right? So we call that as a multiplier modulator. Multiplier modulator. Message signal multiplied with the carrier signal. You get your double sideband suppressed carrier wave. That circle with the cross, okay, multiplication mark, that is called as multiplier modulator. It's a modulator only, right? Let us see what exactly is that. Simple mathematics we are going to see. Okay. What we are going to use here is analog multipliers. Analog multipliers. This analog electronics you are going to study in the next semester. But in brief, to the point of understanding double sideband suppressed carrier wave, I will just tell you very brief things here. Okay. Now, what is an amplifier? You all know about amplifier, right? You all know about amplifier because you are all expert in microelectronics now, right? You all know about amplifier. That's where you study throughout your microelectronics course. Yes or no? Amplifier, 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 common emitter, common emitter, common emitter, right? Okay. So the gain beta of a transistor, the gain of a transistor m of t and cos omega ct is applied as an input to the amplifier, then the output is proportional to the m of t cos omega ct. See here, what is happening here is you have a transistor, and for the transistor circuit you apply this m of t and cos omega ct, and output you get which is proportional to m of t into cos omega ct with some gain. Have you understood this? Okay. You all know that output of a transistor is equal to gain times the input, yes or no? Gain times the input, right? So that means there is a multiplication over there, right? So you have m of t and cos omega ct. Cos omega ct is going to give a variable gain to a transistor. This is what you have seen in your transistor A modulator, yes or no? I have explained you one transistor A modulator, right? Yes or no? Where you have applied a carrier signal at the input and you have connected your message signal to the emitter. Yes or no? Now what happens? Your gain of the amplifier changes according to the modulating signal, message signal, right? So what you get at the collector is input times the gain, and the gain is nothing but your m of t. I have understood this. I am just taking it from your amplifier point of view, right? In amplifier, all of you know, in amplifier, okay, just try to understand this. You have an amplifier here, okay, this is an amplifier and this is your emitter. I am just going to draw one simple RC coupled amplifier. I don't know how many of you know about it. This is a biasing circuit, and here you are going to give, okay, a signal, this signal, and see here now what happens. Try to understand this. This is the output. Now output at this point, suppose if you take a collector current IC, which is equal to beta times IB, right? Which is equal to beta times IB, right? Now see, this IB will be a carrier wave. IB will be carrier wave. That means I am going to connect my carrier signal here. I have explained to you this already, I am repeating it, okay? This is my carrier wave, which constitute base current IB, right? Now your current at this point, collector, is equal to beta times IB, right? Now a typical common emitter amplifier where you don't connect anything except a coupling capacitor here, this beta will be constant, right? Beta will be constant. Now I can make this amplifier as a variable gain amplifier. This is the gain of the amplifier, right? I can make this amplifier as a variable gain amplifier. Gain will not be constant, right? So what I will do, I will make this beta proportional to your m of t. This is what I have told you in my previous class, right? So this variable gain amplifier, what it does is, this beta is we are making proportional to m of t, right? And you can see the collector current is also proportional to this beta times IB, and see beta is proportional to m of t, yes or no? I told you, in variable gain amplifier, we are making beta proportional to m of t. What is your IB? IB proportional to cos omega ct, right? IB is proportional to cos omega ct. Then what is this, tell me? What is this? This is your the DSB-SC waveform, yes or no? This is your DSB-SC wave, DSB-SC wave. Is it not? We can use a variable gain amplifier to generate your double sideband suppressed carrier EM wave. Right, this is the theory behind it, okay? That's what I am trying to tell you about this, okay? Now, nonlinear modulator. See, let us see theoretically what is nonlinear modulator. See here. You can use nonlinear modulator such as semiconductor diode or transistor. See, this NL is a nonlinear device. You know, your diode is a nonlinear device, right? Your transistor is a nonlinear device. Why it's called a nonlinear device? Why this diode is called as nonlinear device? Why transistor is called as nonlinear device? Any reason? See, these are very important points you need to remember. Right? No. No, see, I am telling you, knowledge is supreme power. Try to keep all the small things which will definitely help you in your future. What is nonlinear device? How do you say the device is nonlinear? Exactly, Varsha, you are right. How many of you know about it like Varsha? You see the VI characteristics. Is it linear? No. Even transistor also see VI characteristics. Is it linear? Oh, these are all simple things which can get you into a beautiful job after you graduating this. If people blame our system here, you say studying in Bitsvilla and Dubai, you will not get the job. You haven't got the job in big company. But you don't know these things are going to help you. Remember this. Right? A 9-pointer who doesn't know about basic things, maybe a 7-pointer who knows all these things is the winner in the future. That's why I'm telling you, knowledge is supreme power. Not money, neither position, nor your parents' property, nothing. Take this advice from me. Right? Remember all these small things. Don't forget. Don't think that it is okay. Why forget? No, never do this. These small things are going to help you a lot. Have you understood this? Okay? So go behind money or knowledge? Knowledge. Okay? Fine. See here, what exactly you are doing here? See, m of t, cos omega ct, both are required to generate double sideband EM wave, right? Okay, see here. Now, see this, cos omega ct, see you are just going to get x1 of t is equal to cos omega ct in plus m of t. Similarly, you get here x2 of t, m of t minus of m of t cos omega ct. See, what exactly happens here, you can just see. I'll just explain you this. Okay. See, this, whenever you have a nonlinear device, right, the input-output relation follows a law called as square law, right? It will follow a law called as square law. Okay. See here, if you see this relation, the input-output characteristics of a nonlinear device approximated by a power series, okay, approximated by a power series. That is, y of t is equal to a into x of t plus b into x square of t. Whenever you give an input to a nonlinear device, okay, your output follows a law called as square law, right? That square law is given by, okay, a into x of t plus b into x square of t. That means in this you get two outputs, right? y1 of t is equal to cos omega c t, and m of t, it is given as an input here, okay, and you are going to get this output as, okay, a into x1 of t plus b into x1 square of t. That is a property of a nonlinear device. This you are supposed to study in electronic devices. I don't know how many of you studied it in electronic devices. When you study electronic devices in second year, okay, when you study diode, right, so the input-output relations is going to use a square law. Have you understood this? Okay, I'm just putting it to you in the brief here. Now, how this is going to produce an EM wave, we'll come back to this, don't worry. First, let us know about this, right? So now this y1 of t is actually x1 of t. So what is x1 of t? x1 of t is coming from m of t and cos omega ct, right? See here, this is given as an input to this nonlinear device. This is given as an input to this nonlinear device, okay? And then it is actually subtracted. Can you see here? Subtractor. This is a subtractor, and then what you get is the EM wave. Let us see how do you get that EM wave. See here, something is used here. Something is used here. It is going to be a filter, right? Now see, we need to find out what is the expression you are going to get here, right? Based on the expression here, you need to remove something out of that expression, because what you require is only sidebands here, right? This is a modulator for DSB SC EM wave, right? Now whatever expression you are going to get here at this point is going to be having only two sidebands, but expression at this point may have baseband frequency also, right? I am now putting a new word called baseband frequency. What is this baseband frequency? If I say baseband frequency, what is this? I am putting a new word here. Baseband frequency means frequency of the message signal itself, right? Baseband signal is normally low frequency signals, right? If I say baseband signal, that means baseband signal is nothing but frequency of the message signal. Have you understood this? Okay. See, sometimes I can say modulating frequency, same. Frequency of the message signal, same. Frequency of the baseband signal, also same. All these are same, right? So if I say your signal at this point may have baseband frequency and also passband frequency, right? What is passband frequency? Right? The sidebands are called passband. Now remember carefully here, I will come back to this point. See here, this can easily show you baseband signal and passband signal. Now in this, just remember what is baseband signal and what is passband signal. See here, this is a spectrum of a baseband signal. Why it is called baseband signal? Because it's a low frequency. This is a signal of a, this is a spectrum of a signal itself. Spectrum of message signal itself. This is called baseband. Now this is called passband. Right? Is it not that you are having certain frequency, passband frequency? This is called passband. This is called passband. Right? So this is called passband. So this is baseband, and this is baseband frequency. This one is passband frequencies. So this is passband frequency, this is baseband frequency. And all of you know how you got this spectrum, right? I have explained you. Okay? This is the Fourier transform. That's why I told you Fourier transform is very important everywhere. You can't get away with the Fourier transform, right? Fine. So as I told you, I'll be coming back to this point now. If I see the expressions, at this point, it may have both baseband and passband frequencies. And what is required here? Only passband frequencies. Yes, no, yes or no? Because you are using, you're generating double sideband suppressed carrier wave. So definitely you may need a low pass filter here to remove the baseband signal, right? Yes or no? Right? So we will see what type of filter is used there. Now let us see, I told you this y1 of t, okay, follows the nonlinear device equation, that is square law. Now let us see this. See here, your y of t is equal to a into x of t plus b into x square of t. This is what the nonlinear relation is. Your diode and transistors are going to follow this input-output relation. Now, what is x of t in our nonlinear device arrangement? It is your x1 of t is equal to cos omega c t plus m of t, yes or no? Right? What is x2 of t? Cos omega c t minus m of t, right? I have told you this, see here. What is x1 of t? Cos omega c t plus m of t. What is x2 of t? Cos omega c t minus m of t, yes or no? Okay, now when your x1 of t and x2 of t is known, can you put this in this equation? What is z of t? First write this. What is z of t here? Output z of, suppose if you take z of t here, what is z of t? Output at this point. y1 of t plus y2 of t, right? What is y1 of t? What is y1 of t? Come on, see, simple derivation, don't expect me to do everything on that. A into x1 of t plus b into x1 square of t, right? What is y2 of t? x2 of t, right? Same x2 of t, right? So a into x2 of t plus b into x2 square of t, right? Now, what is x1 of t and x2 of t? You know it, right? Okay, can you simplify this? Substitute everything and can you simplify? Substitute everything and simplify. See what you will get. Simplify this. I have skipped so many steps. Okay? Do it fast. You have to be a little fast in this. Substitute this here. Okay? What you will get z of t? What you will get as z of t? Of course, I told you that I have skipped step. You have to do it. I'm just expecting you to do this. From here to here, there are some steps. Of course, it takes time. Can you solve that? I'm just letting you to do this. Can you solve this? Substitute this. So, see here, what you will get as a z of t? Come on, tell me. What you will get? What are you getting at the output of nonlinear device? You will get this. Z of t is equal to 2a into m of t plus 4b into m of t cos omega ct. Now tell me, in this expression, what should be your output, required output? Whether this one or this one, this is modulator. See, this is not demodulator. Tell me, what is your required output to generate a double sideband suppressed carrier AM wave? This one. This is what actually your output is. Now, how do you get that from this equation? You use which type of filter? Low pass filter or high pass filter, or is it high pass filter? Exactly, high pass filter, yes, right. You need to use a high pass filter, okay, with the cutoff frequency. See, it is not high pass filter you use a band pass filter, because you have to retain only this, right? Have understood this? Only band of frequency you have to remain. See, this is m of t into cos omega ct. See, what is the spectrum of this? A band pass, right? Spectrum of this, the spectrum of m of t into cos omega ct is a band pass, right? So what is the frequency of this, tell me? F plus fc and f minus fc, yes or no? Right, in that case you are going to use a band pass filter which is having a bandwidth of 2 times f. Right, you have to use band pass filter here. It is m of t into cos omega ct. Right. Can you draw the spectrum of this? If I ask you to draw the spectrum, what is the spectrum of this? I did the same problem in the beginning of the class. What is the spectrum of this? Suppose if I want to draw the spectrum of this. Come on, this is very bad. I don't accept this. Right. Suppose your m of t signal is like this, and its corresponding m of f is like this. This is m of t, and this is m of f. Right? This is b hertz, this is minus b hertz. Suppose if we take this in f. Now can you tell me what will be the shape of this? So you will have, this is 2a into m of f plus 4b into m of f minus fc plus m of f plus fc. That means you will have 2a times m of f plus this plus shifted signal, yes or no? This are shifted signals. So your entire spectrum will be something like this, yes or no? Entire spectrum will be something like this. Something like this. Yes or no? Right? The shape, don't go by amplitude, shape is like this, yes or no? Now, what you need to remove out of this? Tell me. To get double sideband suppressed carrier wave, what is required, what is not required? This is not required, right? You require only this. To keep only this, what is required? You need a band pass filter or low pass filter or high pass filter. You need only band pass filter. That's where you will have to use at this point. See. See, you have to pass it through a band pass filter. You have to pass the band pass filter. See. Now, for demodulation, I can use the same technique, right? I can use the same technique. Multiply the signal with the cos omega ct. So, now this is the only modulation process. This is the only modulation process where you use same multiplier modulator for both modulation and demodulation. Yes or no? Right. In modulation also you multiply by carrier wave. Demodulation also you multiply by carrier wave. So, this one device can do both modulation and demodulation. Hope you understood now. Right? That's why multiplier modulator can be used in both modulation and demodulation, and this is called as synchronous detector. Synchronous detector. Okay. Okay, so